Next up, we have David Wiberg, who comes to us from IIASA's water program, and he's going to tell us about some new global water scenarios.
Overfishing and fisheries evolution is certainly a major problem, but of course we wouldn't have fish without water. So let's talk about water. For that matter, Francis, no forest either. So my presentation kind of serves as an announcement for a new initiative that we are now undertaking at IIASA. The title slide basically says it all: Water Futures and Solutions. That means we'll be investigating water futures with a focus on identifying solutions that are adaptive and flexible and robust, and we'll be using as a tool the development of stakeholder-based scenarios, interdisciplinary and multi-sectoral. So that's a lot of language. So we'll go through it step by step, starting with the problems, if I can get this to work. No. Next slide, please. Okay. So what are the global water challenges? Well, we've had several investigations over the past years on what the global water challenges are, so I'll just pick out a few of the points that have been mentioned throughout the literature. 900 million people still have inadequate access to safe fresh water despite progress that we've made toward the Millennium Development Goals. Also, water use is growing faster than the rate of population increase. And we can see this in this plot here. The water withdrawal per capita has been increasing over time. Lately, it's leveled off a little bit as we've become more efficient, but it's still increasing. Consumption is about half of that, but I won't go into that at this moment right now. But to please our Asian NMO, I decided, well, let's look at the overall and Asia. Asia is most of that right now because that's where the population increase has been recently. So, of course, there are spatial differences in where the water demand is. Breaking this down, 25% of the population now lives in areas of physical water scarcity. And in many areas, withdrawals are exceeding the local renewable water resource. This is showed by a map that we developed for FAO's State of Land and Water Report. It shows these areas where the withdrawals are actually exceeding the renewable water resource. And you see some of the regions that have been mentioned already. See northern India, the North China Plain, the western U.S., all of these places where groundwater extractions are greater than their recharge. Increasing and competing demands. Well, obviously, population is still growing. We have 2 billion people more by 2050. Food production requirements will potentially be 70% greater by 2050. And 20% of the world's population has no access to electricity. Now, when Narasimha mentioned yesterday that we have to electrify the population, I couldn't get the image out of my mind of an electrified population. But it's true, we still need to electrify parts of the population, and that will require more water. Industry and energy water uses exceed agriculture in high-income countries. So as the countries develop, they use more industrial water. And what's missing from this picture? Well, ecosystems. They're not well studied. We've been looking at human uses, trying to supply water for human uses. But we've left out ecosystems because we don't fully understand them, and we don't really know what their water requirement is. And so that's another big demand that's missing. The final global water challenge that I'll mention right now is climate change and variability. So this is the mean runoff in the past. This is the standard deviation of runoff, which is quite high. I know it's quite small to show in the picture. This is the percentage change from 1971 to 2000. This was based on a recent project called WATCH, Water and Global Change, where they did multi-model ensemble assessments. And so you see the regions around the Mediterranean, dry areas kind of get drier in general. Wet areas get wetter. Then with this analysis, we could also do the change in the standard deviation, or the change in the probabilities of events occurring. So this was also an advancement in science. However, it adds another global challenge. So now what do we do about these global challenges? We have a number of global challenges. They've been identified in many, many recent studies over the last 10, 20 years. But the question is, how do we manage these? And so what are the management challenges that go hand in hand with these global water challenges? Well, water management must intensify. This is rather obvious. You have the same amount of water resources. You have more demand. We need to intensify our use. We have to get something out of every drop of water. Managing the water sector alone is no longer enough. Water is cross-cutting. It goes across scales. It goes across sectors. And the water resources are increasingly scarce. And water management is risk-based, and this is something that we haven't done very well about predicting in the future. How does the risk change? How does the probability change? We know with climate change that the amount of water will change in places. We know that the risk, the probabilities should change, but we haven't really known how much. There are large uncertainties in the data. There are large uncertainties in the scenarios. There are large uncertainties within the models themselves. And now we're facing a situation where we think there's no longer stationarity. The probability distribution functions will not stay the same in the future, although you can argue that that has always been the case, and now we're just more aware of it than we were in the past. However, what water managers would like to have, of course, is knowledge about how this probability distribution function will change. And that's one thing we haven't yet been able to provide, but we're getting closer with the recent studies. The other question we have to ask ourselves is, what information from science do water managers need in order to manage sustainably water in the future? Well, I can tell you what they would like. They would like a crystal ball. They would like perfect foresight so they could plan their infrastructure into the future. But unfortunately, we don't have it. And we never have it. There will always be uncertainty in the future. So now, how do we plan for management in the future? And I can tell you what we're planning to do with our own Water Futures and Solutions project. I'll lay out an 8-step plan. I know this is a little bit much, maybe, for political scientists. But it's a common approach. We start with a conceptual model, of course, of the system. What are the feedbacks? What are the interrelationships between the different sectors, between the different disciplines, between the different water users? Then we do an analysis of the drivers in the system. What are the trends in the drivers, and how do they interact? How do they interrelate? What are the formulas and functions that define those interactions? Then we develop with stakeholders narratives of the future. How will the future look? What do the stakeholders really want to investigate into the future, and what are their visions for the future? Then we investigate the changes of those drivers using multiple models, multi-model ensembles, so that we can understand the uncertainty within the modeling methodologies themselves. We investigate the impacts using these models, the different management options, and hopefully, in the end, we identify sets of robust and flexible solutions that will work today, but also work into the future under the variety of different possible futures. And finally, of course, and very importantly, we communicate. This has been a topic of the conference, but we need to communicate. We need to communicate with the public. The stakeholder groups help that communication process, but we need to communicate with policymakers, we need to communicate with the public, and we need to communicate with each other within the different scientific disciplines. And most importantly, all of these items are done iteratively with stakeholder interaction. We are building upon experience, though. This is not the first project to look into this. IIASA has quite a bit of experience, and IIASA's research plan is set up ideally for this. Now, yesterday, Francis, you said that you wanted forestry to be in the middle of this diagram. Well, since I'm a water engineer, I put water in the middle of the diagram. But anyway, there are interactions between all these different groups, all these different sciences, and we have quite a bit of experience working with scenarios at IIASA and working with these crosses between the different sciences. Just as examples, one of the biggest drivers that I already mentioned is population. Well, the population program has developed probabilistic population projections into the future. So those give us an idea of not just how population might develop, but the probability of the different scenarios of population development. The global energy assessment has been mentioned many times. Energy, as I've already said, is one of the biggest users of water in the high-income countries. And this year we also released a new global agroecological zoning study for agriculture around the world. Finally, we are the repository for data for the IPCC, for Water and Global Change Project, for the Global Energy Assessment, for the agricultural assessments, for population projects, and for the gains modeling. So we have all this data, we have all this knowledge, we have all this experience developing scenarios, and so we can put it all together now for water. We're also building upon the initial phases of this project. The World Water Scenarios has 2 booklets already out, one on drivers and one on stylized scenarios. I won't go into the details of these, but I'll just tell you that these are products that are already out now, have been released at the World Water Forum this year. We also have experience working with multi-level stakeholder processes in scenarios for Europe. They worked at a pilot area, regional, and pan-European. This is just a result that when it was started, we asked stakeholders what they thought population growth rates would be. Those are the individual lines you see. That was the first step. Then later, when the probabilistic population projections came out, that was the part in yellow that showed, well, our stakeholders weren't very good at predicting population. So after 2 rounds of iteration, we came up with something that was 4 different scenarios that were within ranges that scientists would consider appropriate. Finally, we have experience working with Water and Global Change project with multi-model ensembles with the improvement of scales in these models. We worked with several different land surface hydrologic models and global hydrologic models, and we combined them into multi-model ensembles to produce this type of mapping. They used the same precipitation input, but there's a big range in the evaporation from the different models and a big range in the runoff fraction. So that gives us an idea. It brackets the uncertainty in the modeling efforts itself. Okay, we'll wrap it up right now. Yep. The output that we're trying to get to is a new generation, of course, of integrated global water scenarios and a vision that are consistent with these other scenario processes that I mentioned. We want to develop a solutions options toolbox for scenario-based decision-making and an information exchange network and training workshops. So that will be the output of the project. Thank you very much.